Welcome back from the coffee break. I hope you enjoyed the cake from Lighter. And we're now ready to continue the show. And first up, we have the grand old man of Swedish space, Sven Gran, who's going to tell us everything he knows.
Vad ska den vara någonstans? Någonstans. Fickan. Okej, då må man manövrera med. Okej. Okay. Grand old man. Could have dropped the old, I think. Anyway, telling everything I know and then some. All right, so when I started in the space business in earnest in the 60s, system engineering was sort of what they did in the Apollo program. And it was something I heard about, was talked about. It wasn't taught at KTH for sure, and definitely not in the engineering physics curriculum. So, but everybody talked about it, and it was sort of an honorary title, call yourself a systems engineer. So, well, so I'm going to tell you what I've learned about this profession or discipline by just participating over almost 50 years. So anyway, I hope you enjoy it. So what makes space so special? That's the first thing you have to ask yourself. And then go through some of the spacecraft that I will mention and which I've been part of. And then what is system engineering? And then talk a little bit about system engineering for space and two ideas about the customer constraints and what I call requirements creep. And then something, over the years, I've heard all these management philosophies, the Six Sigma. Well, I haven't heard, I just ignored that. But anyway, faster, better, cheaper, fast track of the small team approach. Anyway, lots of stuff. So some of it was bullshit and some of it was interesting. So let's kick off. So what makes space so special? Well, the system, if you take a one-off satellite, the system must work perfectly the first time in the operational environment, and it's hard to simulate. And maintenance and repair, except for space stations, Christer, is impossible. You can't fix it. You can try sending telecommands, but unless you have some kind of robotic operator, you can't tighten screws. As built documentation must be perfect because there's no hardware to look at, which means that the documentation must be absolutely top-notch. And then you get instant feedback. Well, if something is wrong, it blows up. And then the little sticker there, I'll tell you a story about that. This was in 1972 when I was a tourist at the Kennedy Space Center. I was invited there by a friend of mine in Florida, who was a radio astronomer, and knew people at the Cape. So he said, you have to come down and see the last Apollo to the moon go. And I had this, tourist badge. And Dick was my friend's name. He said, well, talk to Charlie Bell. He works at the coming shuttle program. He will get us in. Charlie Bell got us in, and we got into the VAB, the Vehicle Assembly Building. We took the elevator to the top floor. What was there? The Skylab space station being prepared for flight. And I walked up to and touched the solar panel, the one that fell off. You read up his story. It fell off during launch. Anyway, and then Charlie Bell said, Sven, shut up. Why is that? If they hear you're a foreigner, will be thrown out. So anyway, so I got to see it. And then there was a little cardboard box at the level where the space station was. And I tore off this sticker on it. Because it showed what they had. The box was empty. So they had this zero defects doctrine. Everything, critical space item, handled with extreme care. Around a human-occupied space station, you could certainly understand you had stuff like that. So this is, that's what makes space so special. Something about the spacecraft in this presentation. This is for bragging. Viking was the first satellite I was involved in. I wrote the systems level specification, the customer specification to Saab and Boeing that actually built the spacecraft. It was Sweden's first satellite. It was a particles in the field satellite. All KTH was deeply involved, the Alvin laboratory guys. It was launched on Ariane 1 in a very tough radiation environment. And it didn't have an onboard computer. I said, how can you launch a satellite with an onboard computer? Worked fine. You don't need an onboard computer. Actually, in the beginning of the 90s, NASA launched a spacecraft, a lunar prospector, to the moon. It didn't have a computer either. In this case, it had an electromechanical sequencer. The electromechanical sequencer actually controlled the attitude control, the magnetic coils. And you could, by a telecommand, program it to various positions. And there was one telecommand that was generic system level, that you could turn on the transmitter and turn it off. That was all. Otherwise, it was all work in real time. The satellite was over the horizon for several hours because the orbit was so elliptical. So you didn't need to have stored commands or take down data from other places. Everything could be done from SRAGE. So that's how it worked. And it had single string, no redundancy, because we had promised that it would last only 8 months. It lasted 444 days, and then it gave up. And it was a problem with the power system. But it did its work. And Sweden's first satellite. Then the one I'm the project manager for, first satellite entirely developed by Swedish Space Corporation. And we had an 8-person team. It was a very mild radiation environment. And it will drop out of orbit in 350 years. So blame me for the space debris. And we launched on a Chinese rocket. And we were 8 persons at SSC, and we had another assembly contractor in Arborg, actually, another 5 people. So it's still there. It did its job. You can see it took some really pretty picture of the aurora. And you see the auroral arc and the magnetic North Pole in the top. And then the field line footprint of the field line going through the satellite. So that's kind of neat. And the lady there is Mrs. Wang Fushu of the China Great Wall Industry Corporation, the Chinese project manager. I call her my Chinese big sister. Okay. Then we built a small satellite called Astrid 1, a microsatellite using spares from the Freya project. And this was Freya was a fully redundant satellite, by the way. It had spares for everything on board. But Astrid 1 was a single strings. And we built it from idea to launch in 16 months. And the actual construction took 14 months. And it was built by only 2 full-time team members. The project manager is the president and director general of the National Space Agency, Anna Ratzman. She couldn't go for the launch in Russia because she got pregnant. So she had to stay home and manage the system from home. SSC, that is. We built the second one, Astrid 2, which was a complete redesign. The interesting thing with this, it was completely automated operation of the spacecraft and the ground station. This had a computer, and so did Freya and Astrid 1. And it was also launched from Russia. 14,000 person hours. You could compute how much money that is. In those days, the hourly rate was, well, 1,000 crowns. Then Odin is the big thing. A satellite was launched in 2001. Still works after 23 years. First 3-axis stabilized spacecraft developed by SSC. We specified it to last 2 years. It still works. And it's in the sun synchronous orbit at the terminator, the day-night line, the dawn-dusk orbit. This was a bigger operation, though. About 12 persons worked on it at SSC, and then it was Saab, Scania, and Linköping were the contracting, assembly contractor. Some of the first stuff we did was the ozone hole. You can see that on the picture there. Now, then it did astronomy, and now it's atmospheric or stratospheric clouds, stuff like that. So it was launched by a decommissioned nuclear missile from Russia. $5 million. Worked like a dream. The accuracy of that rocket was really scary. Anyway, the Smart Moon Probe was developed under ESA rules, which was a completely turnaround. You know, there's a saying with contracts from ESA, so little money, so much pain. And there was so much pain. I was chewed out by ESA management every week, told I was an idiot, etc. But afterwards they said, "Oh, wonderful, Sven, you built the cheapest best spacecraft we ever had." That's the way how it's worked with a big agency. But we had to man up, and there are itinerant workers in the space field. But 75 people at the moment. Yeah. By the way, it went to the moon. It crashed on the visible sign in 2006. Some of the basics about system engineering. What is it? Now, let's get basic. A system may be defined as a group of interdependent elements united by a common objective. Sounds okay. An engineer is one who applies the principles of science toward making new devices to serve some useful purpose. Wow, that's a revelation. A systems engineer is one whose new devices are systems. Okay, fine. Systems engineering requires the fact that now it's getting important, the faculty of envisaging a problem from a general rather than a specialized point of view. It is characterized as being oriented towards satisfying the need of a customer. Here's a new element. A customer suddenly appears like a ghost out of the woodwork. And that customer has to be satisfied in some way by what you're doing. So all of a sudden, it's getting interesting. Who came up with this definition? I stole it from a classic, Skolnick's Introduction to Radar System. And so it's about radar systems, actually. But it could be applied to any system. But it's very simple. Then we come to how do you do it? And now, of course, this is the meat of the matter. And it's, you know, sort of obvious also. According to Skolnick, pretty straightforward. You understand the customer's problem, okay? You examine all possible approaches. Yeah, sure. You select the optimum system. Now it's getting difficult. Here you could develop an academic discipline, how you select an optimum system, you know. You make a preliminary design and you examine the preliminary design, see if it meets the requirements, whatever they are. You develop the system, well, that's you. You're done in a jiffy. I develop a system. You test the shit out of it to see that it meets the customer's requirements. And the devil's in the details. So here is, of course, the whole basis for the academic discipline of system engineering, which is taught nowadays. Just a side note. The customer may be something of the don't know squared problem. The customer don't know that they don't know. So that's the role of the systems engineer, to understand if the customer doesn't know that he doesn't know. So anyway, some system engineering philosophies for space. So this is not required, it's constraints and wishes. To think about some space systems. First of all, space projects have many types of primary constraints. Designed to objectives. I wonder if this works. No, it doesn't work. It says to send a man to the moon within a decade is out and bring him safely back to the Earth. John Kennedy said that. So that was Apollo. Objectives, very clear. Nothing else. Get him there, get back, and alive, and beat the Russians. Very, very simple, and very straightforward, and very good. That was very distinct. Capability, Christy would object here, but the International Space Station, it wasn't specified exactly what it was for. It was like building a laboratory building for a university, you know. Could be used for all sorts of interesting stuff. And you should have capability, you should have this much laboratory space and this and that, but not exactly what it was going to do. So sort of purpose is a bit unclear, which was the purpose of the whole thing. It was supposed to be unclear, the exact purpose. Then you have requirements. Well, of course, there was requirements, but typical for profit. If you have a telecom satellite, it should serve this number of television viewers, this number of connections, etc., and it should generate this much money per hour it's working. Telecom satellites are typically profit-driven and technical, detailed numerical requirements. I have designed ones, I know. Cost. Oh dear. This is typical of scientific missions. ESA says, this is a 600 mega euro project and it cannot cost any more. If it does, we'll cancel it. They seldom do, but they always threaten to do that. Then you have the really interesting thing, that is development cost instead of life cycle cost, the space shuttle. Why does a space shuttle have solid boosters and this did have that and the tank? Because it was too expensive to develop a flyback booster, which was the original idea. But to do it this way was affordable. It was sort of a little tricky solution, but anyway. Then, of course, the not uncommon problem, the user, for example, a scientist may not be the person with the purse, and you have requirements creep. How to avoid the requirements creep? Well, you can have a resource envelope and negotiate with the customer. You can have mass volume, power, energy, data rate, memory, blah, blah. And only negotiate the envelope and let the other things inside the envelope to the various suppliers of instruments, for example. I usually show this because this is a system engineering fighting nice to have or must have requirements. And the requirements are, of course, the tentacles coming in through the door of the Nautilus. And Captain Nemo is swinging his axe, cutting his expensive requirements here and there, Anyway, if you worked in the space business, and you know what I mean. And something about management philosophies I've heard over the years. Faster, better, cheaper. I went to a conference in Baltimore in 1994. I mean, this is 30 years ago. And NASA's administrator at that time, Dan Goldin, he came up with this slogan, faster, better, cheaper. NASA's budget has just been cut by 30%. And he had been to the Jet Propulsion Laboratory in California and seen this multi-billion-dollar spacecraft being ready for launch. And he said, we're never going to build any more of those. And then panic broke out, of course. So he pushed this faster, better, cheaper. And they launched spacecraft to Mars following this management doctrine. They didn't work. And then, of course, you can ask why. So here's a guy from the Rand Corporation who gave a talk that I listened to. It was Liam Sarsfield. He describes faster, better, cheaper. The original idea was they have skunk works, no matrix. Oh, what do you mean of matrix? Well, if you have a big organization organized by technical departments and you get people from the technical departments and gather them in the project, that's a matrix organization. So you should have skunk works. Everybody who knows something should be under the same umbrella. Rapid prototyping instead of waterfall development. Well, we know about that in software, and non-space parts. But you should accept the higher risk. This was how it was conceived from the beginning. But as he said, it requires a very smart customer. And then, of course, the saying goes, you only get 2 out of the 3. You get faster and better, but not cheaper. You get faster and cheaper, but not better. And you get better and cheaper, but not faster. Etc. So it's very hard. This paradigm that Dan Goldin put out never worked. You have to think another way. But it was interesting why it lasted anyway. Then the fast track method. As I stole this from a book by a guy called Henry Petrosky, which I think you should read. To Engineer is Human: The Role of Failure in Successful Design. Really interesting book about failures. Design as you go. Used in the construction industry, is applied to space, maybe iterative design, fine. Small integrated team, now we're getting to something interesting. Non-space quality part, not really. 2 out of 3, the FBC. This is the Astrid 1 satellite I showed you. It certainly had a small integrated team, just big enough to be multidisciplinary. It was integrated, no cracks between tasks, all took the responsibility for the system. Minimum documentation. Then I have this quote, which probably people kill me for. And every time there's a failure, the documentation is found to be in order. Quote NASA manager. I don't know if it's true, but I think that usually it's not the documentation, it's what you do behind the documentation, which is the problem. So anyway, small team approach. So small projects, you have an integrated project team and you have subcontractors around it. Larger project, you have a temporary staff and you have a permanent integrated project team in the middle. And then you have subcontractors. So this is a sketch of the project room for the Viking satellite at Boeing. And so the red things are permanent staff. This was before computers. It was only in the last blue row that was a Texas Silent terminal with a paper roll coming out at the time. That's where they did the thermal analysis. Otherwise, they were just drawing boards, and there were engineers sitting there. And there was it was before Wikipedia or whatever, or internet. So there was this big metal cabinet with engineering standard station at the side there. Kind of interesting. And then, of course, you had the glass partition. There was a project manager, engineering manager, and the test manager. And there was a secretary, an elderly lady, looked very stern. And there was a book there with the project rules, including how to treat the customer. That's me. And that was a coffee machine. And the test manager was a funny guy. He had a nail on the wall with a round disc with a hole in the middle with the text rounded to it. And I said, Harry, what's this for? Oh, it's a lesson from the Apollo program. He worked on the Apollo program. Well, an engineer comes in and describes what he's doing. And I will say, have you done this or that, Jimmy? And he says, I haven't got the round to it. So I take down this thing, the round to it, and say, here's a round to it. Silly thing. But Harry had worked on the lunar orbiter, took pictures of the moon before Apollo landing. And the guy, the engineering manager, he had worked on the lunar rover. So this was fun to meet these guys. But anyway, this is what it looked like. So they had the small team approach. And actually, most of the engineers here, the next station in life would be the golf course. They were on the verge of retirement. So they took the most experienced engineers and put on our project to teach us Swedes to build a satellite. Wonderful. Well, then you can talk about project organization, wolf pack or army, all in the house, outsourcing to the extreme. Werner von Braun's outfit in Alabama used to be all in-house, and the U.S. Air Force had outsourced to the extreme. Small team approach. Well, reduced documentation, talked about that. And the core team should follow the project from cradle to grave. And development operations should be in the same team, in my opinion. Maybe that's sort of not what you do nowadays, but I think if you do a one-off satellite, scientific satellite, this is the way to do it. Elimination of contractual layers. This is a bit controversial. And you can absorb the technical risk, and you can get rid of the subsystem level contractors. And you can make this yourself if it's difficult to specify. It's difficult to tell the contractor what you should do. Well, let's do it ourselves instead, because then we can modify as we go along. And you can use commercial off-the-shelf designs. And you shouldn't supervise this experienced suppliers to death. You should, I'll tell you an example. When we bought the antennas for the Freya satellite from Ericsson in Mölndal, ESA were collecting the same type of antennas at the same time. So I said, so the ESA said, yeah, do you want to have a look in the conference room? So we looked in, and there was this many binders on the table. I said, we only get one like this. Yeah, but you only pay for that. Well, it was a standard item, this damn antenna they had made for years. And this guy who made it was a handmade antenna. He had made all of them. So why would we need this much documentation? Was this enough? So Anna Ratzman, the DG of the Space Agency, we took the antenna in a metal box, took the train back to Stockholm. ART should be with the prime. Share risk with the customer, of course, sort of obvious. I should tell everybody what the cost and schedule is. I'll jump this because I think I've overstayed my welcome almost, haven't I? I'll tell anyway. A PI satellite, what is that? Well, a project led by a project scientist, and payload consists of many instruments, each managed independently by a principal investigator. Then you have interface control documents. There's the sort of contract with the project, and the instruments are financed separately from the project. This is what I call a PI satellite. Then you have an observatory satellite. 1 or 2 instruments only. Instruments often built by industry and financed through the project. These are 2 distinctly different projects in terms of management. PI satellite, each instrument is takes care of a specific aspect of the scientific problem, waves or fields and particles and stuff. And the mission degrades gracefully as instruments stop working. And design philosophy could vary from instrument to instrument. They could make a trade-off between radiation protection and functionality, or between parts quality and functionality and mass and stuff. Redundancy and functionality, it's up to them. Freya was such a project. The instruments died at various times. For interplanetary missions, it's different, of course. Observatory satellite. The instrument is as critical to the mission success as the platform. There's no graceful degradation. The instrument needs to be developed with the same diligence as the rest of the spacecraft. And the instrument is often pushing technology envelope and may dominate the spacecraft because it will always be on the critical line, which is good. It shows that the project has the right priority. Pre-development is necessary. Odin, 23 years in space, is the prime example. 3 cheers for Odin. Anyway, thank you.
Thank you, Sven. Exactly on time. We're going to move on to our next speaker. This is Moshe Kiss from KTH. He's going to talk about using balloons to study black holes. Sounds interesting.
Can you hear me okay? Excellent, thank you. Thank you very much. Okay, so my name is Moshe, and I'm, I'm a researcher at the Particle Physics, Astrophysics, and Medical Imaging Group at the Royal Institute of Technology in Stockholm. I guess that kind of makes me a space engineer. I work on instrumentation for astrophysics with a focus on X-ray polarization. Previously, I've worked on a mission called POGO. Some of you may have heard about POGO before. This was a balloon-borne X-ray polarimeter. It was successfully launched in 2016. And these days, I'm working on a mission called XL Caliber. This is a 2nd generation balloon-borne X-ray polarimeter. And that was launched just a few months ago. So, sorry, I'm 1 slide behind. My apologies. So the topic of this talk here is how to study black holes. And if we want to study black holes, we immediately run into a problem, namely that they are difficult to observe. They're very distant, they are compact, and they have no direct emission of light. Many of you are probably familiar with this image here, which is the region around the supermassive black hole M87 star. So even though this is one of the biggest black holes, a supermassive black hole, it required essentially an Earth-sized telescope to create this image. This is the Event Horizon Telescope, and it's using interferometry techniques to create this image. So is there any way that we can use just relatively small balloons to study black holes? Direct imaging is, of course, going to be impossible, but we can obtain geometric information, and the way we do that is to use polarization. So what is special about polarization is that it's sensitive to the history of the emission, how it was created, what geometries or magnetic fields or what space-time it encountered before reaching our instrument. So we can take an example from Earth, which is direct sunlight. So as the sunlight is emitted, it's unpolarized. But if it's reflected off a surface, like for example, the surface of water, then the reflected component becomes polarized. And you want to use your polarizing sunglasses to protect against the glare of this reflected component. And it turns out that the same is possible also for astrophysical sources, also for X-ray emission. So here we see a binary system with a black hole and a visible star in an orbit around each other. And the material from the visible star is accreted and it's forming the accretion disk that's moving in towards the black hole. And the direct emission from this region is unpolarized. But just as we saw for the surface of water, if the X-ray emission is reflected off this accretion disk, then the reflected component becomes polarized. And this polarized emission can tell us something about the black hole. So we want to use polarization to study X-ray binary systems. And this here is showing an artist's impression of what this can look like. You have the visible companion star in orbit around the black hole, and you form the accretion disk. Once in a while, you have relativistic jets that are emitted perpendicular to the disk. And at least in radio wavelengths, we can kind of resolve this image, this region. So in this image here, you see the kind of resolved X-ray region for an X-ray binary system. But the black hole region that we're interested in this case is only 1/1,000,000th the size of that. So we cannot image it directly. For the emission from these regions, there are different emission models, and we think that polarization can help us constrain these emission models. So we're seeing some examples here of different models for the emission where you have different reflected components or scattered components and so on. An example of such a binary system is Cygnus X1, and this particular system was studied with XL Caliber during the summer 2024 flight. So XL Caliber is a Compton polarimeter, and it means that it's using the Compton scattering technique to measure polarization. And this is based on the fact that photons have a higher probability to scatter perpendicular to the polarization of the incident flux. So the name of the game in X-ray polarimetry is to measure a distribution of photon scattering angles, and it creates this modulation curve that you can see here, where the polarization information is encoded in this simple sinusoidal curve. The phase of the modulation curve is giving us the polarization direction, and the amplitude of the modulation curve is related to the strength of the polarization of the flux that we're observing. In XL Caliber, we're using a beryllium scattering element for these Compton scatterings, and it's surrounded by a pixelated detector of cadmium zinc telluride, CZT. So the way this works is that you have the X-ray emission coming from your distance source that you're observing, for example, such an X-ray binary system, and we use an X-ray mirror to focus this emission onto a relatively small polarimeter. So the X-ray mirror gives us a relatively large collecting area, but by having a small detector, we have a small background. So the polarimeter itself is about the size of a milk carton. And we call this a second generation X-ray polarimeter. That simply means that we're focusing X-rays. And because it's difficult to focus X-rays, we get a very long focal length, about 12 meters focal length. So you start from this relatively small milk carton sized polarimeter, but you end up with something that's this big. This is the XL Caliber payload and launch configuration just before the launch from S-range. And on the left-hand side, we see the X-ray mirror that's focusing our X-rays. This was made by colleagues in Japan. And the X-rays are focused onto the polarimeter that you can see on the right-hand side, made by colleagues in the US. And the polarimeter is shielded by an anti-coincidence shield made here in Sweden. So this whole thing is very big. As you can see, it's pointed with the Wallops arc second pointer, the NASA WASP system. So this is the pointing system that allows us to point to these sources in the sky and track them as they're moving in the sky. And the total mass of this system here is about 2,000 kilograms, with the very big length resulting from the focal length of the X-ray mirror. So just to get the X-rays onto this very small polarimeter, you need this whole structure here. So let me just say a few words about the anti-coincidence shield that we built in Sweden. So the beam from the mirror is coming in, and it's going through a tungsten collimator where it can impinge on the scattering element, the beryllium scattering rod, and that's where these Compton scatterings take place. It's surrounded by the CZT detector, the pixelated detector that allows us to reconstruct the modulation curve. And all of this is surrounded by an anti-coincidence shield made of BGO scintillator. So BGO has a high stopping power. It's very good for shielding against the type of background that we experience during the flight. The shield is read out by photomultiplier tubes from Hamamatsu. I think we have some colleagues from Hamamatsu here in the audience today. And this whole thing was designed, manufactured, assembled, and tested at KTH. Through the KTH Space Technology Lab, we have access to a vacuum chamber and a climate chamber, so we can test and certify these components to make sure that they're surviving the launch conditions and flight conditions. So the launch is from the S-Range Space Center near Kiruna in northern Sweden. You can see an aerial view of the balloon pad in S-Range. And the balloon we're flying with is 1 million cubic meter helium balloon. So at launch, you have this water drop shape, a relatively small thing. But as you climb towards the float altitude, 40 kilometers, it gets bigger and bigger. It expands more and more as the ambient pressure is decreasing. And at the float altitude of 40 kilometers, you reach this 1 million cubic meter volume, which is about twice the size of Globen Arena or Avicii Arena here in Stockholm. And of course, we want to go as high as possible because the X-rays we want to observe are otherwise absorbed in the atmosphere. So the launch was on the 9th of July, actually my son's birthday, and we flew in the westerly direction towards Canada. So it took us, we had almost a 6-day flight to get to Canada, where we landed near Kugluktuk in Canada. So during the flight, the instrument was working very well. This plot here is showing the rate impinging on this anti-coincidence shield that I was mentioning as a function of time during the first few hours of the mission. So when we launch, we have the relatively low background rate that we expect on ground. But as we ascend through the atmosphere, we get a higher and higher background rate, eventually reaching the maximum at about 20 kilometer altitude. This is the so-called Reginer-Fotzer maximum, which is the highest background level. And as you go higher, towards the float altitude of 40 kilometers, it actually decreases a little bit. So our float background rate was about 6 kilohertz. And using this anti-coincidence shield that I was talking about and event selection techniques, we can see a weak signal emerging from all this kilohertz level background. We can see roughly a 1 hertz signal emerging. And that is seen in the plot in the bottom here, where we have the polarimeter rate, so the good hit rate, the valid hit rate as a function of time. You see several days of observation throughout the flight. The red curve, the red data points are showing the signal, and you can see the signal rising and setting, just essentially following the elevation of the source in the sky as it's rising and setting during the day. And this is superimposed on a very flat and constant background that you can see in the black data points. The background, residual background level is about 0.3 hertz, so our peak signal to background ratio is about 4:1. And this is about an order of magnitude improvement over first generation X-ray, balloon-borne X-ray polarimeters, such as the POGO mission I was mentioning before. So we know that we see the source, we have an unambiguous source detection, and the next step is then to get to the polarization, and this analysis is ongoing. The polarization is very interesting in this particular case because we have previous results from a mission called XP. stands for Imaging X-ray Polarimetry Explorer, and this is in a complementary energy range. So the XL caliber energy range is about 20 to 60 kiloelectron volts, and XP is a slightly lower energy between 2 and 8 kiloelectron volts. So in the X-ray XP data points that we can see here, we see the polarization degree on the vertical axis and the energy on the horizontal axis, and their data points seem to favor an increase, a slight increase with energy. Now, we were very interested to see if this trend carries on in the XL caliber energy range, because this is what gives us the handle on these emission models. So an increasing polarization as a function of energy would hint towards a type of emission models called lamppost models. Whereas if the polarization actually stays constant through this energy range, it's more favoring a different kind of a different category of emission models called corona emission models. So this is how we can use polarization to learn more about these black holes, even though we cannot resolve them. So the landing was very successful. That's a good thing about flying a balloon-borne instrument, that it can land with a parachute and you can recover it and make improvements and fly it again. So we were very happy to see that we didn't land in water and we didn't land on rocks or anything. There was no visible damage to the polarimeter or this mirror, which is one of a kind basically. And we have already successfully recovered the hardware from Kugluktuk in Canada. So we're refurbishing and getting ready for a reflight. And the next flight is hopefully going to be from Antarctica. This will be no earlier than December 2026. And the point of flying from Antarctica is that you get access to the astrophysical sources that are on the southern hemisphere. So currently we're flying from the S range. We're seeing the northern hemisphere with some sources there, and there are different sources on the southern hemisphere. And because you're always above land, you can get a much longer mission duration, much longer flight. The current record duration is 57 days, and you can make several circumnavigations of the South Pole, as shown in this image here. So you have much more observation time to observe these sources, including some interesting black hole candidates. And with that, I thank you for your attention, and I think I can take questions over beer.
Thank you so much. We continue with the next speaker. Anna Hekma from OHB here in Kista is going to talk.
Yes, thanks a lot. So my name is Anna Hekma. I work as a systems engineer at OHB Sweden here in Kista. I'm not from Sweden and I haven't studied at KTH. I'm from the Netherlands and I studied at Delft, the aerospace engineering faculty over there. And the topic of today is systems engineering in space. And when I think about systems engineering, I usually, as a student, I usually thought about satellites directly. So I thought maybe we can just spend a few minutes on saying, okay, what is a system actually? And I want to do this by taking the Arctic Weather Satellite. That's a project that OHB Sweden has been involved in for a couple of years, and me myself as well, as an example, and looking at the different parts or systems that our satellite system is built upon. So I should have put another picture here. I don't know if Jan is still here from Geisler. So a system on a chip. That's really the smallest system that I could find on our spacecraft, and it's basically what he explained, like a super tiny 5 centimeter footprint integrated circuit where you can have all the typical interfaces, requirements, a customer, all the things that a system should look at. But then at a really small footprint. Combining a bunch of these would turn into an onboard computer or a PCB for an onboard computer. And this is the PCB that we use for the Arctic weather data handling unit. And here you see again, you have to think about mass, about power, about thermal aspects, and really at a small form factor still. Going up a little bit is where we come to the unit level. Here you see the GPS receiver that we use. And there a unit has to be tested, usually for shock, random vibration, thermal vacuum, and all, again, interfaces to the rest of the system would become very important. A subsystem is then combining a number of units. Here we see a propulsion subsystem where you have a number of thrusters, a power supply unit, piping, a tank, and this is again a big system already, but not the system that I would think of. And this is where we come to the space segment. So this is still not what we would call the system level, but it's just a segment of the system. And this is the Arctic weather satellite. You see, I will come into a little bit more detail, but you see the solar panels, you see the propulsion subsystem here on the back end. And this is then part of what I would call the Arctic weather satellite system or mission. And here you get really into a lot of interfaces that are important. So you have the space segment, of course, but the ground segment, as important as the space segment to understand what is going on. Up there, you have the launch segment. Of course, you need to get there. And the end users. Again, the end users might not necessarily be the customers, but they are going to use the data that your system is providing. A little sidestep here where our system actually became part of an even bigger system. This is the stack of the Transporter 11 rideshare mission from SpaceX. And if you look closely, you can see it's over there. You can see the Arctic weather satellite sitting here as one of over 100 payloads that were launched in one go on this Transporter 11 flight. And then, as one system is not enough, we're looking towards systems of systems, where you use, for example, Galileo and a low Earth position, navigation, and timing element to combine really a lot of different systems into an encapsulating system of systems that can provide services to hundreds, maybe thousands, of different users and billions of people that use this type of services. So systems are really all around us. And when we see people applying at OHB Sweden and want to become a system engineer, they usually think about the satellite and the mission. But my and our recommendation is really also don't forget that there is a lot of systems that are maybe a little bit less exciting at first, but still very important also to learn your skills as a young graduate, to start your system engineering experience with a smaller scale and then building up to whatever you think is interesting, be it big or be it small on a chip. So that was a short introduction on systems engineering. Then maybe a little bit obligatory slide on OHB Sweden. So maybe surprising, but we are actually not all that far away. In Kista, we have about 130 people working there. We have big clean rooms, and we built a full range of small satellites in our clean rooms there. On top of that, we're also building propulsion subsystem and AOCS subsystems for bigger satellites. And as Sven Gran already mentioned, we've been to the moon. We've been going to comets. We're really going everywhere from Kista. Then the example that I want to go into a bit more detail is the Arctic weather satellite. And that started really with a question of, okay, how can we improve weather forecasting? You're all living in Sweden, so you know that the SMHI app is not all that great. So we want to improve that. The problem is that most of the current meteorological satellites are actually geostationary orbits, So they're about 36,000 kilometers above the Earth. And they're only seeing the equator of the Earth. So our idea, well, it's not our idea, but you can use polar orbiting satellites that are usually that are flying then at a lower orbit, so about 600 kilometers for Arctic weather. And that allows you to see much closer to Earth and also much better resolution over the poles. The Arctic Weather Satellite is a project that is funded by the European Space Agency and has participation from a large number of countries. And that's also where this space engineering, space systems engineering is really important to how to maintain all of those interactions with suppliers, with subcontractors, with partners. And that is an important part of the systems engineering. So then I have a few nice pictures, or I think they're quite nice, of the assembly, testing, and the life of the Arctic Weather Satellite. So here we start quite small. So this is where we have the panels of our platform. You see a lot of harness, so cables inside the spacecraft. You see a radio. On the bottom left, you see the battery that are charged by the solar panels. And this is where we start our system integration of a satellite. And just before we close our box, we want to make sure it's clean. And that's what you're seeing here. These are our product assurance and quality assurance colleagues cleaning the satellite. So to make sure that no debris can enter into, for example, the payload. Because if you have a sensitive payload, you don't want it to be disturbed by some debris that we left while working in the clean room. Then this is where two parts of the satellite come together. On the bottom here, you see the platform. That's the box that contains all the computers, the power supply units, all the AOCS sensors and actuators. And on the left, on the top, you see the Arctic weather payload. So it's a radiometer, and you see a small reflector that is actually rotating and making a scan of the Earth every second. So this is what we would call the marriage, and here we combine then the payload and the platform of the satellites together. And then you have everything built together, and you need to test it. So here, one of the tests that we've been doing is electromagnetic compatibility testing. We did that in Germany in a test facility, and here we were specifically looking at how the platform could impact the payload. So if you were looking, and if you're looking at the Earth, you want to see what's going on with the weather, you want to make sure that you're actually looking at the stuff from the Earth and not at some signal that you're yourself producing on the satellite. Then, of course, you need to get your satellite to space. Here you see we've now attached the solar panels that were not present in the previous picture. It also looks a bit smaller, but it's still the same satellite. And we put it on a plate that is then later placed on this big stack that I showed before on the Transporter 11. And you get a nice picture like this. So from California, a big Falcon 9 rocket, and you see your project go up. It's very interesting. But then, of course, the first science data. And I don't know if you remember, but in September, there was a big storm over Middle and Eastern Europe that was wreaking really havoc there, and was a lot of rain. And we actually managed to capture that on one of the first days that we switched on the payload. And you see here that you see the caption, so the altitude changes, and you see that we can measure the humidity, so then the amount of water in the atmosphere at different altitudes. So this is really already on one of the first days showing the information that this meteorologists need to improve their systems. That's the Arctic Weather Satellite now flying around and in operation, but we still have a few more projects coming up. And here we also see that we are building satellites that are similar but not the same. So we try to reproduce or like reuse the platform that we have and put on it various other instruments so as to reduce the costs, make it better, make it faster, and maybe even a little bit cheaper. So we have a hyperspectral imagers. Oh, sorry, that's this one. A hyperspectral imager. We have very high resolution cameras. We have a radio, almost like a detection center for radio signals. And Aurora D is actually going to look at another part of the Aurora phenomena that we've seen before. So there's many more projects coming up at OHB Sweden. And I just want to thank you for your attention. And yeah, we can take some more questions over a beer.
Thank you, Anna. And next up, we have Malin Åkermo from KTH. She's going to come up and talk about materials for space.
Hello? Yeah. Oh. So, hello everyone. My name is Malin Åkermo. As you can see, I'm a professor in lightweight structures, actually, at KTH. I come from the same department as Christer, but to be honest, I have never worked with space. I hope I'm allowed to stay here still on the stage. But I wanted to tell you a little bit about what we are doing right now to improve the lightning of the materials. And I think that is very important for you dealing with space as well. So there we have a shared interest. So more than 50% of the commercial aircrafts of today are made out of carbon fiber composites, the structural parts. They are very stiff and strong, and in many applications, we can reduce weight with 50% using composites. But there is actually more to it. Can we maybe use them for something more? That is questions we've been asking ourselves. And what I'm going to show you today is a collection of different projects we are running at KTH. So it's different groups. And mostly it's about carbon fiber, but not always. But we can start with the carbon fiber. So when we talk about multifunctional composite, normally what they do, they carry load. They should be strong, stiff. But what we want to investigate, and what we have investigated lately, is if they also can be used for energy storage, if they can change the shape of the material, so we can use them for example morphing, strain sensing, or different kinds of sensing, not only strain, and energy harvesting. So all these different things are things we have explored lately to different levels with different materials and in different teams. And I will try to summarize where we are right now based on this. So if we start with the energy storing, the idea was initially we look at a lithium-ion battery, and you see that there is a positive electrode and negative electrode. There are lithium ions that need to go from left to right, and it becomes a battery. It works more or less a little bit like this. Yeah, it's self-instructive. So the question was, can we use carbon fiber for the positive electrode? Can we use a carbon fiber also for the negative electrode? Can we have a polymer matrix in between as electrolyte? The problem is that electrolyte is a fluent today, and a fluent can't carry load, and we want to make something structural. But this is a project I've been running for maybe 10 years now, research groups at KTH, different departments, and also at Chalmers. And today we are at a stage where we can intercalate lithium ions into the carbon fiber. You see the structure up to the left. We have developed a semi-structural electrolyte that can carry load and that actually transports the ions through. We have a package that is a battery that consists of carbon fiber and this electrolyte. And it has a 45 gigapascal longitudinal modulus, which is a little bit low. We want to be at least at 75 or above 100 if we can wish, but we are on the right way. And we can store 40 watt-hour per kilogram material. We want to increase that to double, but at least we are on our way there to make a battery that is also a structure. So we can build maybe a beam that holds something up, and at the same time, it stores the energy we need. Considering sensing composite material, we have tried with a lot of different materials with promising results. We have used inbuilt fiber optic sensors. That's not maybe so new, but building them into the composite is quite new. We have printed graphene on the fibers to see if that is gives us some interesting signals. And we've been measuring on the carbon fiber as they are. But today I'm just going to show you some examples, and then we're going to look at the test we've done with multi-wall aligned carbon nanotubes. So in principle, we have a multimeter that measures on the multi-wall carbon nanotubes, very small. And as you tension it, we want to see that the resistance go up, as in this curve. So the material looks like this. You see that it's 2 nanometers, 2 micrometer, the small line there to the right. These are the carbon nanotube material we're using. We attach it to, in this case, a glass fiber material. So you see that the white material has become quite dirty or blackish. And this is the initial material, and then we cure it and we can tension it. If we measure the resistance while in blue, while we strain the material, we see as we pull it, the resistance go up, the relative resistance. And when we let it go back, it goes back again. So this is the total raw signal, not filtered or polished in any way. And you see that we have a very good resemblance. And in the same way, we can detect resistance difference due to temperature changes according to a model. Let's see. We can also see what happens in the composite. The composite material consists of fibers, but also a matrix. So if we put like a fluent matrix among these carbon nanotubes, we will see different phases. As the blue line here is the resistance again. As the temperature goes up and the matrix is impregnating all this carbon nanotube, we see that the resistance goes up, and then it goes down again when the material starts curing, and we can see all the different phase changes. So it has shown to be very good for monitoring also the manufacturing process. So what we want to do is have a material that we can put inside a composite, and from the cradle to the grave, we can follow what's happening in the material. We are currently looking at pressure sensing, thinking that we want to have it on the outer side of a wing structure, for example, and be able to measure the surface pressure. And we are exploring if we can do structural health monitoring with these materials. That was sensing. Then we go for shape changing. This is such a hard word to say, especially on a Thursday late. And I want to start by just showing these bistable tape springs that probably a few of you already have seen. This is Gunnar Tibet has worked with a couple of student teams at KTH with these self-developed deployable tape springs, and they work like this. So with that, I want to show that they're quite fast in developing. Here we can see a movie from Gunnar and the team. Yeah, you see. It's in slow motion, and you see how they kind of automatically develops. Can I make that work as well? Maybe. Yeah. So this doesn't require any energy to develop. They are, you just start it, they will develop automatically. The team working with structural batteries, they have found another way of working with morphing. As you intercalate these lithium ions into the carbon, they actually, the carbon fibers swell a little bit. Let's see if I can make this. So you see that the layer with the most lithium ions inside, it becomes a little bit longer, which means that the material actually, see if I can see it. Yeah, it bends. So it changes its shape. And I will now try to see if I can make this video work as well. And please pay attention to this is in hours and minutes and not microseconds as before. Let's see, but you see as the potential decreases and increases, that the current goes up and down. The composite to the right in your picture there, it bends. It takes hours. We need to speed it up. But this is something the aircraft producers are interested in, because they want to be able to fill some gaps while they're flying in order to make the aerodynamics better. But we need to be faster. Sometimes faster is good. Except for that, we have worked with energy harvesting, and this is quite tricky. I asked the guy who's in charge of this if he could explain it to me in a simple way, and he couldn't. Not in a simple way. But what it's all about is that we have kind of a piezoelectric behavior of this material, but it's not piezoelectric, it's more piezochemical. So when we bend it, we get a current. So the mechanical load, the mechanical displacement is transferred into a current, which means that you can if you can make this material flutter a little bit, vibrate, you can generate some electricity. So that is something that is on very low TRL level. And of course, you understand that this will not give us the solution for the world problem in energy, but maybe we can at least keep the lamps, keep the light up on the lamps in an aircraft. Except for those materials that you saw, we are currently also looking for new multifunctional material systems. We want them to have some kind of unique properties. It could be good mechanical properties, tension properties, so that maybe they can, if you pull them a little bit more than the elastic region, that they actually relaxes back and seemingly becomes cure themselves. That is material we're looking for at the time being. The white material you see consists of nanocrystals made from cellulose. The fibers are produced by aligning them with from the flow. And these materials have very low CO2, which of course are very nice for us. But they also have good electrical properties, meaning that they are not electrically conductive, but they have good thermal conductivity, which is quite rare in a mixture that is hard to find. And this, together with potential particles that we can put into the matrix system, we saw before that radiation could be a problem in space. That is something we are looking into, if we can kind of dope the plastic together with fibers to make the properties multifunctional and extraordinary. So that was all I wanted to say today. Thank you for listening and allowing me to stand here, although it was no space. And courtesy to the different teams at KTH, the structural battery teams, been around for a long time. The tape spring teams, the different students all the time, and the sensing composite teams. Thank you.
Thank you, Malin, and you may stay on stage because we're continuing with a panel debate. I'm also going to ask Sven and Anna to come back up on stage for the panel debate. We're going to see how we're going to set this up. I'm thinking we can stand up, have a more dynamic panel, and also Christer, who volunteered to come and be on this panel as well. Oh. Oh. So we're now at the end of the program part 3, and we've said we'd take about half an hour to discuss system engineering requirements for space applications. And after that, we will be going to the pub. But for now, I'm going to change so that in Zoom we can see the people speaking instead. Blank out the screen, and in Zoom. Okay. I'm going to take this microphone and then we'll pass another one around to the panelists as they answer questions. So in Zoom, the listeners can see you. In here, you can see them right here on stage. I'll come in on the side. Good idea. Yes, I think this works. So I think we in the audience have some youngsters who still want to be space engineers, and we also have some that have been space engineers, maybe. But we're aiming this panel for those who want to be space engineers, and I think one thing they wonder is, what should they study? So we can start with Malin. And in this case, we're thinking a space engineer, I mean, could be a researcher.
Yep.
It could be someone that works for Sven or Anna building satellites. But it could also be someone that goes up on ISS. These are different aspects of doing space, right?
So what they should study? They should study something that they burns for, are interested in. I mean, that's always number one. But of course, I hope they want to study mechanics and mathematics and all the basic stuff, because we need to understand them. But I also think that we have this data-driven methods coming in that will be of great use in the future. That's the kind of from the educational perspective, but I guess Sven has much better answers considering exactly what to study.
Well, I mean, that's that's a $1 million question. I think that the important thing is not exactly what subject you pick when you go to school. The most important thing is to burn for the subject, and that you love space systems. Then you could be mechanical engineer, electrical engineer, software developer, whatever. But it's the fun thing of being part of a team that develops a product that does something useful. And that is not only true for space, it's for any industry. You know, when something rolls out the door, we built it and it works. That's all you need.
Yeah, I fully agree, of course. I think we need people that are also like technically curious, like what to find new solutions, to find the things that you might not think of. And I see it even in our team that we have the young new people coming in with AI ideas and with really the next level that even were not so common a few years ago. And the other thing I think that's very important to become a good engineer or space scientist or is also everything outside the curriculum, right? I'm not sure if I'm allowed to say it here, but I think it's also important to develop as a person and as someone who can collaborate and you can work together with people, because teamwork is also very, very important, I think.
Exactly. That's why I have the space pub afterwards. Well, it's not so much to add, but I think, you know, if you want to work with space, you can do it with almost any education. So if you like space, you select courses which has space in it because it's fun. If you later kind of realize, oh, this might be fun to work with space, I'm sure you can have a good chance to get a job at a space-related company anyhow, or you can bring space into the company you are working with, because as I said in the very beginning, space is becoming part of everything today.
Thank you. So next question is, what do you look for in a person when you're hiring? Who can do this way, this round?
Well, I haven't hired many.
Well, you're hiring PhD students.
Yes, I'm hiring PhD students. I've had a few. So you look at the person. I think. I mean, to some extent, you look at the grades, what you've done, but I think it's more important that it's a good person, which is someone you can work with. It fits in the team. So there are many aspects, and hopefully someone here has hired more people than I have and might be able to.
Yeah, I can, as specifically then for system engineering, what I highlighted a little bit in my previous presentation as well is someone who has already a little bit of expertise maybe on one of the parts of the system, so that you can start with a base somewhere where you feel comfortable. Let's say you studied mechanical engineering, then you can be a very good space systems engineer, because you have this strong background in mechanical, but then at the same time you learn something about flight dynamics, and you also learn something about thermal, because yeah, so that's one thing. The other thing is also to be flexible. I think as a system engineer, we see that you need to be able to sort of adapt, and if your team is lacking some competence in AOCS, you need to do the effort yourself and study, maybe take the book off the shelf and look at, okay, how do I actually make the absolute pointing accuracy? How do I determine that? So flexibility is also an important thing, I think, that we look in system engineers.
Sven, have you hired anyone?
Yeah, I hired plenty. I hired Christer as an astronaut. Well, I mean, we were a committee of 4, but still, Christer said was exactly the criterion we used on him, because we said that this guy go out and have a beer with. And that's the criterion for a good astronaut, you know, because it's somebody you can work with. Well, I was thinking about something completely different about, you know, what takes a good system engineering. And a couple of years ago, I made some book recommendations at the KJ Space Center website. And there was one thing about one of the technical wizards of the Apollo program. His name was George Lowe. I can't remember the name of the book right now, but you'll find it. His
philosophy was management by asking questions, system engineering by asking questions. And never, don't criticize, ask questions, and never pretend you know something when you don't. Ask questions. And I think that book is fantastic. I can't remember, but if you Google it, it's on Amazon. It's about George Low, L-O-W. So anyway, that's my recommendation.
So I'm thinking, yesterday I was having 5 interviews for a PhD position. So it's very fresh in my head. So we found 2 candidates. What popped out when it came to those 2, one of them, we saw the first one, we saw that he was really interested in the subject. He wanted to do it. His eyes were shining. So we saw that he had energy that would take him through the difficult times, because if you're a PhD student, you will have difficult times. And then there were another guy. He had clearly good analytical skills, which also popped. I mean, you are all good students and we can all learn new things. But if you aren't able to analyze what you're doing as a PhD student, now I'm talking about PhD student, if you can't analyze it, that might be things that are something that is a little bit harder to learn. So therefore I look particularly for that.
Okay, thank you.
I also think it's important you look for people who can work independent. That is another important aspect.
So that ties into the next question.
Uh-huh.
So how would you build a team?
How would I build a team? Well, you need a team leader who is not going to impose much, but really lead by example and kind of also be a good follower. Actually, you need to be both a good follower and a leader, and then you find the people who can help solving the tasks, the big tasks you need, which probably need some specialists to do that. But you need people who can work together. You're really putting difficult questions here. You have better?
Yeah, I'm thinking maybe to find also people that can take responsibility, and that you can agree. Okay, I will do it, and I will do it properly, so that you know also as a team that you can trust on that one and build on that person doing what he says is going to do, so that when everybody does that, then you build something together. Sven?
Yeah, you should look for people who cover each other's back. I'll tell you an example. When I was managing the Freya satellite, we had project meetings on Friday mornings. Why did we have them on Friday mornings? It was because we would discuss what we're going to do next week and go home and forget about the project over the weekend. But my fantastic moment was one Friday morning, one of the team members said, I woke up at 3 o'clock in the morning and I suddenly realized that I know how to solve your problem, and pointed to somebody else. I thought, this is music to my ears.
Yeah, but that's true. So how do you build a team? I'm thinking that it's quite important to have an atmosphere that has a high roof, for what you say in English, so you are allowed to make mistake, and you can think out loudly without being punished or being it hurts somehow. So you can have an open climate for discussions. I think that is a good start as well for building a team. And then fika.
Keep the microphone at that.
And I think maybe on like catching on to that is also that you are what do I want to say? That you allow everybody in the team to voice their opinions, and that you don't have to, and I really like that in Sweden, where you can basically go to the CEO and say, I have a good idea, and that's being listened to. Whereas in some countries, of course, you have much more hierarchy, and you're never supposed to say anything if you're not at the same level as someone else.
Pass it back to Malin. We're going to take the next question. So we already touched upon this. Sven talked a lot about what is a system, and so did Anna. I wanted to dig a little more into this. What is a system? Because the definition I was taught is that it's the level above where you're working. That's the system. Since the question is here, what does it take to be a space systems engineer? And every engineer is going to ask, well, what is the system? What are the boundaries? Like Anna showed us that, yes, but then there's the launch system also. That you need to think about this as well. So how should we set up the boundaries? What is the system?
That's so hard. I mean, the system is a kind of the system you're working with is the system you're responsible for, where your boundaries are that you're responsible. But of course, then another one is responsible for what's coming outside. So maybe the system is the communication between the different the different teams, the joining of them. It might not be your responsibility, the entire system, but communicating your part is part of the system. Maybe.
Mm-hmm.
Didn't you guys listen to what I said? It has to have there has to be a customer. You know, you have to build something for a customer, somebody with a purse that pays. That is the definition.
So otherwise it's just research?
It is something else, but it's not something that systems engineers do. They work for a customer, they deliver a product. That's the industrial definition of a systems engineer. Then you can have political systems and economic systems, etc. But you're talking about engineering here.
Educational.
Yeah, exactly. I would just try to be a bit facetious.
Yeah, not really much to add.
Well, I mean, a system can be anything or everything is a system, right? Maybe just if you have a single unit of something, then it's maybe not a system. And otherwise, as soon as you have more than one thing, isn't it a system? So you ask me, what is a system? Well, basically everything are systems, I would say, except for, well, single pieces or units.
Okay, all right.
And to go further, is it important?
I'm not sure. We can
How we
set up a
define it.
system to study if we find a customer.
The traceability of requirements.
Yeah, well,
That's exactly how you do it. You have a requirement on top, you design for it, and you test it, you verify it, and you deliver it to the customer. That is how you define it.
But I must say that we see more and more commercial customers that don't have requirements, or at least they haven't written them down as a requirement spec. Exactly. We have to, but then it's for them it's still a system, even though they didn't write down the requirements
If it
themselves.
doesn't work, they won't pay.
no, I mean, all these pieces are important, but is it important to define what is a system? That is my question.
When you do sustainability analysis, it's define what's a system, at least according to the methods they're using, which is also a little bit scary because it's so easy to go to limit yourself and do something bad outside of your own system. So yeah, you're right. Everything is a system.
All right. Moving on to another question. And again, Sven, of course, already talked about this, but so I'll let you other guys speak first. So different management paradigms. You could do NASA, you could do ESA, or you do Swedish space, or something else. Maybe work for Elon Musk. So which management paradigm would you prefer?
I can't answer to this. I'm not working in space. I don't know.
Oh, that's an easy out. Okay.
You mentioned the Elon Musk, or at least like, but don't be afraid to fail. And I feel that in my job currently, okay, we can fail a little bit, but not to the level that Elon Musk is failing, because our customers would not be paying anything anymore. So I think it would be quite interesting to see also for to have more of this just go and fail big. But we see a lot of European small launchers that are trying to do the same. They're failing a lot, and let's see. Hopefully, they're also producing some quickly with their with their tests.
Okay.
I would say they're not failing fast enough. I mean, Falcon 1, they failed 3 times, right? They forced, they succeeded. I don't think any one of our European companies yet have failed 3 times. So they're not working fast enough. No, I'm not sure I would like to work for Elon Musk. I mean, I think it's probably a hell of a tempo. And I like to work in the academia, but clearly he has a very high efficiency in his company, and we need to find much higher efficiency how we work with space in Europe for sure. And that's it's a little bit too much of the old big dinosaurs who are running it in the continent.
Yeah, and I can maybe also dig into or catch on to what Sven mentioned is having these small, let's say, the least possible layers between the customer and the people that actually do the work, because then you can actually also build a relationship with the customer and have a trust, and they know that, okay, even if you don't fulfill all the requirements to the dot, the system will still perform enough and good enough for the money that you're paying. Well, it can be that you have 5 or 6 entities between the end customer and the one that you're working with, or your level, and then it's impossible to do it. And then everybody is going to go onto the dots and the T's of the requirements, because you don't know who's in the end evaluating it. And if you don't have this trust between the customer and the people that are doing the bulk of the work, it's going to cost much more, and it's going to be probably long lead times.
Give Sven the mic.
Yeah, I was thinking about the Smart 1 moon probe that we built for ESA. The proposal to ESA had 335,000 working hours. 335,000 working hours. I mean, you need to have a pretty well-organized team to spend that kind of time reasonably. So it has to be organized, and it has to be managed, in a rather strict fashion, friendly but strict. And of course, unfortunately, he's not here, but the retiring CTO of OHB Sweden, Peter Ratzman, was the project manager of Smart 1, and he's a hero.
Yeah. And he still talks about how difficult the relationship was with the customer. So yeah, exactly.
Could we see if we have any questions from the audience? Raise your hand and we can come with a microphone. A young budding space engineer has a question.
I'm Jörgen Städje, technical journalist. It seems like you need to recruit a lot of new technicians. How will you get young people interested in technology when there's very little of technology in school today? I have written several thousand technical articles, but today it's kind of impossible to publish a technical article in Swedish in a techie magazine because there are none. How do you recruit young people when the technology is just, well, not there?
Thank you, Jörgen. Who wants to? Mister, go for it.
Well, the young people, they don't read the magazines, right? You have to write where they go and read, which is online and these things places. So I think we are reaching out, and actually more and more people, we do get more and more students starting at the technical universities. We open more and more student slots there, right? I mean, today there are at least twice as many who starts today than when I started, which is almost as long ago as when Sven started 60 years ago. But But so it's an effort we never can stop doing. And I think we are working on it. And of course, you want to have the best students to become engineers, but we cannot only have engineers in the society either. So we need to have good medical doctors and economists, and I would say even politicians.
So I agree. My daughters are in the age where they have started university, a few of them, and I mean the grades are not low. There are a lot of people who want to get into the education, so that is not the big problem. But I think a problem is that we are lacking in the technical education. We are lacking a lot of females. We are losing the 50% of the competencies in Sweden are not there. Not that much, at least. And I haven't seen any development in the subject where I'm teaching. And that is sad. At KTH, we also talk about recruiting from maybe families that still doesn't have a very academic background. And there are areas, of course, where there are a lot of talent that we do not find. So we can do better. And I think we can find really talented people among the minorities, maybe.
Yeah, I can pick up on that. Yeah, for example, in the student satellite project MIST, which has now been going on for 10 years, horribly enough, we've had a constant level of female participation at 20%. Sometimes it goes up to 22, sometimes down to 19. Right now, it's sort of on the uptick, but it sort of hovers around that level. But I think that, and that's usually aerospace students. Then, of course, if you look over the different disciplines at KTH, it varies a lot. But this is true. But otherwise, I mean, there's some really, the ones that come up, and I see of the Swedes that come from Sweden, they're pretty clever people. I can't complain. And they want to do all the fancy stuff. So I don't know what, there are not enough of them, but the ones who are present are good. Not so worried.
Yeah, I think also what was said before, like to get to reach people where they look, and like things like TikTok or other forums, or I think in OHB Sweden we also sometimes have school classes coming by. I mean, these are, I think, the efforts, but they've probably been going on for a long time, also in Sweden. So how to get even more people, I'm not 100% sure.
Okay.
Thank you. I'm wondering a little bit about how you see the difference in competitiveness between like Swedish students within system engineering competence compared to international students in Europe or in other parts of the world. Do you see any like difference in level of expertise or competence, both in academia but also in the industry, specifically within system engineering areas?
It's difficult to say. I must say I haven't recruited all that many people. I think that there is also at KTH quite a big, like this collaboration, lots of these student projects that are ongoing. I see that from maybe more Southern European countries, there the focus is more on the hard analysis and like really being good at doing the calculations. If the one is better than the other, I'm not sure. I think you need both in the end. Very political correct answer. Yeah. I don't know if any of you want to say something more, maybe.
No, I was
not even.
no.
I can just give you some statistics on my student satellite project. So I've had over 200 students worked on it over the years, and there 40% of them are Swedish citizens. 30% are from the rest of the European Union, and 30% are from the rest of the world. So most of them are not from Sweden, which is interestingly enough. So It gives you, and as I said, 20% are women spread out all over these three categories. So anyway, it's not bad. So I mean, these are students at master's level, so it's pretty.
Before you pass the mic on, Sven, I'll give you the chance. Do you need any more students?
Yeah, but right now they are sort of coming through the door, every day. And I have a hard time keeping up at the moment, But if you have a gem, send it. I'm sorry.
So
about being
anyone
a
who
bit-
is interested, come talk to Sven.
On the statistics part, I think we're roughly the same. I think more international people work at OHB Sweden right now than Swedish nationals, and about 20% female. So in that respect, it's a good reflection. We also see that we have a few internship positions open. We also get a lot of applicants for that. So yeah, the
And
future
how
is
many of the girls have worked for me in the MIST project?
a lot, I think.
Yeah.
So how many of your personnel come from the MIST project? Do you know?
Ooh, I would not know. Maybe it's,
Something between 5 and 10.
Hmm?
Yeah.
So that's the way to get your foot in the door.
yeah,
Gia,
Miss-
for example?
Exactly,
Yeah.
exactly. Yeah.
Ludvika?
Yeah.
Agnes?
I didn't know. You see, quite a lot. So Miss students.
So one last question from the audience. Okay.
Well, it's rather a comment than a question. So I was having this same conversation with my girlfriend at the city of the space city in France, in Toulouse, 2 days ago or last week, about this problem with lack of participants from the female side. We were looking at the pictures and the whole history, and there have been historically very low numbers. Well, the problem I have, I was in the academia and then I was working for a couple of years and now I'm back in academia. So the problem I have seen in my environments so far in the companies here in Sweden has been so that most of the times the female participation has been from either as a financial project manager or as a technical project manager or as a line manager. What else? Most of their participations have been in the management level because it might have been a perspective, in my opinion, that getting to the managerial positions defines sort of a leadership or a better participation, which reduces the participation towards technical roles. So as a lead designer or as a CAD designer or as a test engineer. So this is something I have witnessed in my field, in automobile, in Ludvika, in energy field, and also in other fields like gas turbines and stuff. So this is something I have witnessed. Maybe this is something to take into account when promoting these roles and educations in our society for the future. Thank you.
Did you have a question for the panel?
Well, this is a comment.
A comment,
I just
yes.
wanted to contribute to this since this is a discussion. Yes, thank you.
Thank you. Do we have any other questions? Last chance. Okay.
This question is directed to Sven. If I remember correctly, you said that you were in what was it? You were part of the group. You were part of 4 launches or 3, was it? Yeah. You said. Yeah. As someone who have worked in 4 launches, do you have any tips or what was it again? Do you have any advice for anyone who might want to do the same in the future for students?
Wait for the mic.
Well, I mean, you nowadays, of course, small satellites are you don't participate at the launch site. Transporter 11 flight, for example, there was no supplier there. They just have to deliver the satellites and they just launched into space. But if you're on a bigger project, you actually have to go to the launch site. Then you have to be part of the AIT, Assembly Integration Test Team, because then you actually go to a launch site and participate in the work, the test work. The test engineers usually get to do that. And of course, it's so I mean, for example, I spent with my whole team for the Freya satellite, which was launched in 1992 from China. We spent the whole team. We were with all the experiments. We were 20 people. We spent 50 days in the Gobi Desert. So I mean that was an experience. So I don't know what to say, but it's. You said there was no evacuation.
Time out.
No,
All
this,
right,
this
okay.
is just the door alarms.
Okay.
The doors
But
are
anyway,
open.
I can't really say what, but it's important that people, if you want to advance in an organization, you should have tasted the real stuff. You should have worked on that level with hardware and at test campaigns, launches, and stuff like that. And one should be shy of people who go straight to the top. How can you give an example? The lady who is head of the Swedish National Space Board, Anna Ratzman, she's resigning in a month after 6 years of service. I hired her. She worked in the satellite project that was launched from China that time, and she really served that, a grunt job, every day. Then I promoted her to manage the Astrid 1 satellite, which was built in 14 months. She couldn't go to the launch site in Russia because she became pregnant. That's okay. But so she managed that and launched that. Then she went to Ericsson for a couple of years, and then she came back and took on a management position. So she went the whole cycle through the grunt technical work and then into management positions gradually. So that's the way to do it. You have to start at the bottom and work yourself up.
Well, I mean, another possibility, if you're interested in working with launches, try to get a job at S-Range. I mean, now, since many years, they're still launching sounding rockets, and they do that regularly, but very soon they will start to launch rockets big enough to launch satellites. So look for a job there.
Some KTH previous students working there. So you can talk to them, I can give you a tip.
Maybe also on the launch side, we when we have launches with OHB Sweden, so we've had GMST launch, we have MOTS launch, Arctic Weather launch in the last 3-4 years. We usually have one mechanical engineer who's responsible to go really on the launch campaign. So it was not, so if you're talking about 60 to 150 kilogram satellites, there's still people going to the launch site, not all that many. But usually it's a mechanical engineer, an electrical engineer, and a system engineer usually to do the final testing before we board the spacecraft on the launcher itself. And now the next time we're going there, we actually don't even bring a project manager anymore because we figured out that project managers are not needed at the launch site. So don't become a project manager. That's what I want to say.
So should we let that be the final words? Don't be a project manager if you want to be a system engineer. That's right. So let's thank the panel. And we're rounding off, but we still have some announcements. So the final part for today is the networking pub. So I ask Malin Andreasson to come up on stage and tell us how to get there.
Yes, how to get on the space pub that we have prepared. You just outside here, up the stairs, and there's Tristan. We have made a nice patch for everyone to buy today in the bar. We have made some food, and yeah, you're super welcome.
Thank you. Let's go. And with that, we close the space rendezvous. Please leave your name tags either here or in the pub so we can collect them.